Good. I always find it easier, rather than distributing the 1/2, just multiply both sides by 2. Multiply both sides by 2. It's easier that way. But you can distribute. It's just a pain, I think. Okay? All right, so hey, you ready? I didn't type up the definitions today for you. Sorry. I know. 4 new words. Inscribed angle is an angle with the vertex on the circle as opposed to the center where we saw central angle, right? So this is a vertex on the circle and sides that contain chords. Sides that contain chords. So I left this here so we could draw a picture, right? So draw a picture. So we're going to draw an inscribed angle. Maybe look something like this. So let's say this angle is 35 degrees. So the vertex is on the circle, and it's made up of 2 chords, right? Not necessarily congruent or anything like that. All right. Intercepted arc is the arc that is formed by an inscribed angle. So this right here, it should be a different color maybe. That would be the intercepted arc. Make sense?
Yeah. No.
What part? Of those 2 definitions. You good? Okay. An inscribed polygon is a polygon. You might be able to know already what this is. It's a polygon in which all vertices lie on a circle. So again, we could draw another circle here. Give me some polygons. What are some polygons? Triangle, quadrilateral, pentagon. Those are all polygons, right? So let's just draw a quadrilateral here. Doesn't necessarily have to be anything congruent. That's an inscribed polygon. And then a circumscribed circle is the circle that contains the vertices of an inscribed polygon. Okay? So 4 new words there. You might want to put them on a list just so you can memorize them this weekend. The circle that contains the vertices of an inscribed polygon. It's called a circumscribed circle. All right. We have some theorems that go along with this idea, these definitions. The measure of an inscribed angle theorem. The measure of an inscribed angle is 1/2 the measure of its intercepted arc. Oh, we have an inscribed angle right here, and here's the intercepted arc. So if this is 35 degrees, this theorem then says that this arc is actually how many degrees? 70. Now, you think, oh, that's kind of weird, isn't it? But let's think about this. What if I put the center right here, and you can do this or not, and I kind of drew the central angle from that point. See, it does look a lot bigger than that 35 degrees, doesn't it? So, kind of makes sense if you think about it. Mine might be a little off, but it does when you draw a picture like that. All right, so 10.8. If two inscribed angles of a circle intercept the same arc, then the angles are congruent. So let's just draw a circle here and I'll show you what I mean. That's a pretty lousy circle, but you'll get the point. So I'm going to draw one inscribed angle here. I'm going to label that A, B, this is going to be D. Then I'm going to draw another inscribed angle from here that goes to the same endpoints. Yeah, let's call that C. So, if two inscribed angles of a circle intercept the same arc, which they do here, they intercept the same arc. Just put them right on the basket there, please.
How many do you need?
Okay. So that means that these inscribed angles are the same measure because they share the arc there. Make sense? What?
Yeah.
Which part, Catherine? Let's clear it up.
The part where the
Wait,
top
so like,
This one?
yeah, so the 70 is like,
If I were to go from the center, yeah, if I were to go from the center, it looks,
and then
because remember when we went from the center, the arc and the angle were the same. But when we go off the center, ladies, that makes the theorem says when you go off the center, that angle measure is half of the arc,
okay, no matter what.
no matter what. Because if you think about how we're repositioning that vertice, it's going to make that angle smaller, and it makes it half
But you're
the
keeping
size.
that point.
Pardon me?
But you're keeping like the,
Yes, yes,
okay.
yes, yes. Maeve,
for angle like D and C, so those angles are congruent?
these angles are congruent.
Okay.
Yes. So we can mark that. This angle and this angle would be congruent.
Are the sides congruent or no?
I can't say for certainty. I want to say yes, but I hate to say yes unless I know for sure. I'd have to look that up. I think so.
Yeah,
It would seem like they would have to be.
Yeah.
Yeah. In a right triangle, if a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. That's the only way it would work. So let's draw another circle. So if we have a right triangle inscribed in this circle, so I'll draw a right triangle here. It's kind of hard when your circles aren't exact. Mine's a little bit off, but what it's saying is anytime you have a right triangle inscribed in a circle, the hypotenuse will always be the diameter. Because that's the only way it would fit.
Oh, okay.
My circle's a little off. Conversely, so you need to know it the other way too. Conversely, if one side of an inscribed triangle is the diameter, then you know it's a right triangle. Okay? Yes. Emma.
But that other one was the angle, so like 5 on the arc. Did you say the lines like are congruent or aren't?
I think they have to be.
But like what if?
I can't say for sure.
What if C was like over by the, like over to the right?
Like if C was up here? Yeah, then that's true. They probably wouldn't be.
Yeah.
Because C could be up here.
Or it could be like 5.
I don't know. I have to look that up. That's a good question. I don't want to say yes for sure, especially in math, because I don't know what's coming higher up. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So, let's go up here to our picture. We have a quadrilateral, don't we? I did that on purpose. Let's label it D, E, F, and G. D, E, F, and G. So this theorem says it can be inscribed in a circle if and only its opposite angles are supplementary. So I'm going to say here from above, we can say that angle, the measure of angle E plus the measure of angle G is equal to the measure of angle D plus the measure of angle F and they are both equal to 180. That's kind of how you might see it in the book. Make sense? So we just have a few practice things based on all this information. Okay? Turn it over. Find the indicated measure in circle C. So this one, well, the first part's not too bad.
I thought you meant circle with C.
Find the in circle C, find the measure of angle D. So what do you know here? What are you seeing in this picture?
Oh, wouldn't that
This
be?
one would be half of 100.
It is. It's half of 100. It's half of the arc measure. So it's going to be 50 degrees. Half of 100. The measure of arc AB. So I had to kind of think of this look at this for a minute. So we're looking at the measure of arc AB. If I could figure out maybe if I draw this here, if I can figure this angle out, I can figure that out, right? So no, let's look at what if you draw this here. Let's look at what we have here. What do we have here?
90 degree angle.
We do, and how do we know that this has to be a right triangle? Because of the diameter. So let's put DB is the hypotenuse. Just as an explanation to yourself. So therefore, it's a right triangle. We have a right triangle ADB. It's the diameter, however you want to look at it. So if I were to realize that this is 90 degrees, I could find out angle D, couldn't I? By subtracting. 180 minus 90 minus 35 equals 55 degrees. So the measure of angle D is equal to 55 degrees, which makes the measure of arc AB what? 110, double. So you kind of have to look at some of these pictures and decide, I know this is the diameter, I know AB comes off of angle D, so maybe I can figure it out that way. You see it?
Yeah, that I just, yeah.
So how would you know that arc AD is double arc AD?
Because this is this one right here, right? An inscribed angle right here. If you look at it like this, it's not coming off the center, is it? So it's an inscribed angle, and anytime you have an inscribed angle, the arc is twice the angle measure. All righty. Find the measure of arc KN and the measure of angle KMN. What do you notice about the angle KMN? So if you look here, the mark that we need this.
Oh, they're the same.
Yeah, what's the measure of this, first of all? Arc KN. So this is 52, so KN has to be what? Double it, 104. You see it? Because it's got to be double the angle it comes off of. So then, look, then this also comes off of that same arc, doesn't it? And we learned from the theorem 10.8. Theorem 10.8. The angle measures are the same if they come off the same arc. So it has to be 52 degrees. You guys see that? Okay. Find the value of each variable.
Oh, aren't they like this? It has to equal 1.
The opposite angles of an inscribed polygon have to equal 180. A quadrilateral, the opposite angles.
Oh, weird.
See, I know it's different than what you want to think. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary.
So like 100. Okay.
So we would say, all right, theorem 10.10, opposite angles inscribed in a quadrilateral. quadrilateral, are supplementary. I know I'm abbreviating there. This is quad here, quadrilateral. So we would say this x would have to be what? 180. Or excuse me, 80. X would have to be 80 degrees. And here, y would have to be what? 120.
Oh, I get it.
Which is strange, you know, what we're used to. But the other thing you can think about is those are not, it's not a parallelogram, right? So they don't necessarily add to 180, these two, which is kind of what you might be thinking. So here is the same thing. Opposite angles add to 180, so we could just say 7x plus 5x equals 180. Mm-hmm. 12x equals 180. X is equal to 15. And then you could just do the y's. 17 plus 19, what does that equal? 36 equals 180. And y equals 5. Cool?
Cool.
All right.